Morning, everyone. This is our final day. We have 3 lectures in the morning and 2 tutorials in the afternoon. The first one, Magdalena is continuing with calabiometrics from neural networks. Thank you, Magdalena.
Thank you. So good morning, everyone, and welcome back to this last lecture in the lecture series on string theory complexifications, Calabi-Yau manifolds, and Ritchie flat metrics. So the plan for today is that I will continue from where I stopped yesterday and talk more about the details of these machine learning methods, and also have a bit of discussion of the things that people are attempting to do now. So what are the more advanced problems that people are trying to solve? But let's start with summarizing what we did yesterday. So the topic was to use machine learning to predict Calabi-Yau metrics. So we will train some neural network that will give us the Calabi-Yau metric. And this can be done in different ways, so that our choices will determine the architecture of how we design our machine learning model. So we might either want to predict the metric directly, which is what I will focus on today, mostly, or we may want to predict the Kähler potential, since we know that the Calabi-Yau metric will be a Kähler metric. We can do that. And also because we have this, this way of constructing algebraic metrics using this Hermitian matrix H, we can predict the H matrix. Then, so we encode that in our neural network architecture, in particular in the number of outputs, that's the nodes in the output layer of the neural net. And then we encode the physics constraints or the math constraints that we want to enforce. So for example, the Mohr-Champire equation or the Ritchie flatness of the metric into loss functions. And then we train the network using standard machine learning techniques such as stochastic gradient descent and backpropagation. And the important thing here, which is a bit different from other machine learning exercises, is that the trained neural net that you get is really the thing that you're after. So if you're after the Kähler potential, say, then your neural net will be the Kähler potential, and you can use that for computations that involve the Kähler potential, and similarly for the metric. Okay, so today then we'll talk a bit more about how we actually do this, what it looks like when you run one of these packages, and I will focus on the CY metric package, which is the one that I know best. I will say something about how this is structured and what kind of, what it looks like if you look a bit under the hood. And then I will go to these advanced methods. And then in the tutorial this afternoon, you will of course have the chance to try these things yourself and to play with these tools. Okay, so now we're zooming in on one of these packages. This is the CY metric package. It's written in Python. It also has parts of it written in, it uses some functionality from Mathematica, and it's also using some functionality from Sage, which I'll come back to. But basically what this is that it's a package which has point generators that can sample points for you on different kinds of Calabi-Yau manifolds. And then it has machine learning models, which can, that you will use when you construct your neural nets and you train them. So the package is structured in classes that encode these. And these classes inherit then from TensorFlow, which is the machine learning library that we will use. So in particular, these machine learning models, they inherit from TensorFlow. The point generators have nothing to do with machine learning, so they don't do that. And then, of course, there are various functions that are written in this, that are included in this package that can do various things for you. So they can set up the model, compute losses, and so on. So if you look a bit at the structure of the package, if you look at the Python code, then you will see that there will be various files. They will include bits and pieces. And for example, here is an example of the standard point generator, or the highest level point generator class, which generates points on the quintic, say. Okay, so then there will be computations done here. So some of these will be numerical and some will be symbolic, and there are libraries for that. And then I've already mentioned yesterday that one of the things that we will need in these computations is to compute gradients, both for training the network, which is standard in machine learning, but also to compute, for example, from the Kähler potential what the metric is. And then we can use these routines that are available in these machine learning libraries to do that as well. So this is something that is very nicely encoded in these packages, in this package. Right, so then also there are some tricks which really you should ask Fabian about, because he's the one who has written this and he knows what the tricks are to play. But Gide, of course, also is knows these things very well. But if you want if we want to have a machine learning package that should give us Calabi-Yau metrics, and that should be competitive so that it's better than Donaldson's algorithm and Hedrick's functional minimization, then we want it to be fast and we want it to be performant. So using these function decorators is something that you can do when you write Python code so that the functions compile faster, if I understood that correctly. So it's tricky to make Python. And in JAX, so there is another, there are other packages. So one is CYJAX, and then they instead of using these function decorators, they use this JIT and to achieve the same thing. You want something that runs fast. So this is not something that you need to think about when you use the package, but if you want to write a package like this on your own, then these kinds of tricks are the things that you will need. So if you have some other problem, but you want to use this kind of, you want to write some package of this type. Okay, so let's look a bit at the problem at hand. So I will focus for now on the Fermat quintic. This is not at all a necessary restriction for the machine learning methods, but just to stay with the kind of examples that we've talked about so far. So we have a Calabi-Yau manifold. It's given by a quintic polynomial in P4, and I've chosen the simplest quintic polynomial you can think of, so just the sum of quintic monomials in the 5 homogeneous coordinates of the ambient space. And we want to use CY metric to find the Calabi-Yau metric on this. So our input then for this package is that we will take points on the Calabi-Yau. So this means that our neural net should have an input layer with 10 nodes, which are the real and imaginary values of the coordinates of the node. And you might say here, okay, well, dealing with a Calabi-Yau threefold, should I just input 6 values then, because it's just 3 local coordinates? But the way that the code is written, we actually input these 10 values instead. And the information about the Calabi-Yau hypersurface in this is encoded because these, as I described in the last lecture, these points that we have are constructed in such a way that we encode this information. Yes?
For the input, you have to solve what it is.
Yeah.
You plug it around.
So you can do that. It will give you something, but it's just meaningless. So what you will do, and what we will see when we will see that momentarily. I'll come back to that question. No, but you can check. There's a function that you can check whether the point is on the Calabi-Yau. So that's the thing that I will show. Yes.
What could happen if the metric becomes something?
Yes. And so you can get whatever, right? It will just not be meaningful. Yeah. Okay, so then, but good question, and I will comment on that a bit more. So the output will be the metric predictions. So this is a Hermitian metric for a three-dimensional, a space of three complex dimensions. So it will have 9 entries, so a 3 by 3 matrix. So if you're predicting the full metric, then you will have 9 nodes in your output. We also have a metric ansatz where you're basically predicting a Kähler correction to the metric, and then it's just one node that it's the output, which then corresponds to the correction to the Kähler potential, which is one function. So the experiment that we will now do is that we will then generate points, we will create our neural network, we will choose a metric ansatz, we will select our losses, and then we will run the model, and while the model is running, we will go and have T. Depending on the complexity of the model, it takes, from a couple of minutes on my laptop to run a model for say 10 to 20 epochs, up to an hour or a couple of hours. Okay, so let's look at this in a demo, and I'll see if I can manage to do this. Where is my point? This is stupid. Ah, here I am. Okay, so here is a demo that I will just walk you through. This is something that you will do in more detail in the tutorial. So can you see this? Maybe I need to increase the size. Visible? Good. Okay, so here we have, we want to work on the quintic. What we do first is we import some libraries. We import TensorFlow, NumPy for the numerical computations, something that's called pickle, which is something that we use to pickle our data. You store your data so that you can read it later. Okay, so what happens here? So the first thing we do is that we import our point generator because we want to generate points. So we do this like this. Here is our package, C1 metric, and then we define our Calabi-Yau that we want to work with. So here I just want to have this very simple quintic Calabi-Yau. So I just have my monomials as being the 5th power of every ambient space coordinate. And I have the coefficients of that being 1s. I choose the Kähler modulus. There's just one Kähler modulus. I choose it to be 1. And the ambient space has 4, is P4. This is encoded here. And then we initialize the point generator, and we generate some points using these commands here. So if we want to check now that these points are on the Calabi-Yau, then we can do that, which is done here. So there's a function called cy condition. You feed in the points, and then you should check that this gives you a small number. So this checks the distance from the point to the Calabi-Yau hypersurface. And we see here that we get very small numbers. So these are all okay. So then if you have a random point and you just want to test whether this is on the Calabi-Yau, then you can plug it in here and see that it is on the Calabi-Yau. So here it's this method that James described yesterday, where you have in your ambient space, well, it's basically that. So in your ambient P4, you sample points, you sample 2 points, you connect them with a line, and then you solve for the intersections with the Calabi-Yau hypersurface. This is something that works on the quintic, obviously, and I will talk a bit about how we can generalize that method to other kinds of spaces later on. So it's that standard method for generating points, and it's one of the methods that are encoded here.
You specify the Kähler, so you just specify the class, or you actually specifying?
We're specifying the Kähler modulus, as far as I know. I'm not sure. I think there's an option of either keeping the volume, is there an option of having the Kähler modulus not fixed in the text? Right. So yeah.
So the original battery and
We'll come back to that.
Okay.
We'll come back to that. Yes. So I mean, here we're fixing the Kähler modulus, which means that we're fixing the volume, and we do that because we want to stay in the same Kähler class when we're training. But principally, you can switch that off. Okay. So we have generated our points. So here I just generated a few. Maybe we want some more, and then now we want to set up a machine learning network to look at this. So what we do then is that we work with the data that we have generated. Then we include some of these helper functions that will help us put the data in the right form so that these functions work. And then we go to set up the model. So what we want to do here is to define, what loss functions we want to have and how we want to trace the training of the model. So these are called callbacks. So they are basically these error measures evaluated on the model. So we have them here, and their names are not, most of them are understandable. The sigma loss is actually the Monchampère loss, and vol K loss should perhaps more be called Kähler class loss, but that's what they are. Okay, so we have defined what kind of things we want to keep track of when we're training. So then we're setting up the network. We're specifying the number of layers we want to have the network, how many nodes we want to have in these layers, what activation function, the number of dimensions of our Calabi-Yau, so 3 here, the number of input nodes, that's 2 times 5 for the real and imaginary part of the 5 homogeneous coordinates, and the output. And then we just build it using standard TensorFlow and Keras routines. So TensorFlow is a machine learning library. It has functionality for how to build your neural networks, and here we are using that. So here we have our neural network, and then we want to use this for the purpose that we have, which is to learn the Calabi-Yau metric. So then we are calling these, we are selecting these metric ansatz, say, one of them here for our training. And we do that by calling this function here, or this class here. We're creating an instance of the class mult_fs model, which is the metric ansatz where you have your predicted metric being the Fubini-Studio metric plus something that you learn with the neural network. So this is the one that we have here. And then you train this, setting up, you choose how long you want to train it for. So 1 epoch corresponds to running over all the mini batches, and also a second part of the training loop, which has to do with preserving the Kähler class, which I will come back to. And then we can look at the results here. So we see what's happening to our loss. Maybe here I want to zoom out. So we can look here. Here is the Monchampère loss over the training, evaluated on the training set, which are the orange points. So these are the points that we're feeding into the neural network. And we see that the loss is going down, which is nice. It's going down from 0.12 to 0.02, so it's a factor of 6, and over 50 epochs. And then we check the same thing for the validation set or test set, which are points that are unseen during training. And then we can check similar things for the Kähler loss. So here we see that something funny is happening with the Kähler loss. It's initially going down, then it's going up, and then it's going down again on this. So this is also on the test set here. So remember, this is an ansatz here that is not guaranteed to preserve clarity. So it is, what's this showing us is that during the training, we are leaving Kähler class of metrics, and we're going a bit wild and doing things, but then eventually we're coming back to something that is close to being Kähler. These are small numbers if you compare to the numbers here. And similarly, we check the transition loss, it's going down, and here is just a way of presenting how these error measures are related to each other. So you should really read this as coming from, we start about here, and then these losses, these error measures are going down both for the sigma loss and the Ricci loss. Okay, so this was, it was not as easy to see here as I had hoped. So luckily I have this in the slides as well. Okay, so that was a quick run through of what it looks like when you're doing this, and you'll look more into that on the tutorial. So let's look a bit more in detail in what was done here. So we were first building a machine learning model. We used that using TensorFlow. So it's nothing fancy going on here. We're just setting up layers in the standard way. We're choosing their width. We're choosing the activation function. And we are then constructing a neural net in using, for example, this sequential method of Keras. And here we are, I haven't really experimented a lot with other layers than having dense layers. They seem to work very well, but of course that's something that might vary. So what do these metric answers look like? Here in the example, we saw this particular, this multiplicative ansatz here. There are different answers that one can choose. So one would be to have a completely free neural net, so where we don't tell the computer anything about what it is that we want to have. This is bad for different reasons. So one is that you can have, you really have to, the network has to learn all the variations in the network. So it can be, the numerical value of the metric components in different points can vary a lot in size. So maybe that's not something that you want to have in a numerical problem, because it makes it hard to learn quickly, at least. Also, it doesn't know anything about celerity. It doesn't know anything about being positive definite or so. So this is probably not the wisest choice, but it's something that you can do. And it may be something that you might need if you want to generalize this to something something that is very much less constrained than the Calabi metric. All the others are variants of the same idea. So you take the Fubini-Studi metric, which is something that we can compute, as you saw in the last lecture, and you add on a correction to that, and that correction can look differently. And these are just included as choices that you can pick from. All of them, just looking a bit under the hood again, all of them are encoded as classes then that, so as TensorFlow classes that inherit from the standard model of TensorFlow. The loss functions is something that you can choose, as you can choose these. So maybe I didn't actually point to that, but when you're setting up the network, and as you will see in the tutorial, you will have to choose these constants here, alpha. So how much weight you give to the various losses during training. So if you set this vector of numbers to be 1, 0, 0, 0, 0, then you will only train with the Monchampère loss, and you will forget about all the other ones. I should say that the Ricci loss, because it involves these computations of 2 extra derivatives, it's switched off as a default, but you can turn it back on if you want to use it. And then these are the things that I just showed. So you just put things together and you train the model, and you get these kinds of results. So the first one there we saw those are the plots that I just walked you through in the Jupyter notebook. The second one is for this Kähler addition to the neural net, which is, if you look at this, if you want to compare this, you can see that learning the addition, instead of doing this, if you learn for the phi network, you have you learn this function phi here, which is the correction to the Kähler potential. You can see here that this is something that is faster to learn. So if you look at the scale here, you see that one I have to train for 50 epochs, the other for 30. I get down to the same accuracy in both in the error measures, and I also get down to the same value in the losses. Yes, that's true. So you see here, so for this one, for the phi, I did have the Kähler loss on, but it doesn't do anything. So if I would plot the Kähler loss for the training, so here it's just for Kähler loss and transition loss, it's just plotted for the validation set. But you see here it's 10 to the minus 15 on the Kähler loss, so it's really 0. It's just numerical fluctuations. Transition loss, on the other hand, is something that we do need to have, because even though we as humans would immediately say that, aha, this is a function on my space, the neural network has no idea that this is a function. So it can give you something that does not patch up correctly. And this is something that that I talked a bit about yesterday when I mentioned the bihomogeneous and holomorphic networks that Gide has been working on. Because there you enforce the functionness of the Kähler potential using a clever way of handling the input data.
Is the overlapping
No, it's the metric. It's the metric, and this is an important distinction with what is done in Gide's network, and it's also something that people have thought about more recently. So one can say that with this phi network, it works nicely. It gives you, in most cases, completely reliable and good results, but you do need to bear in mind that the computer does not know, does not necessarily give you a phi that is a function. Yes?
What we did there, I mean, we're using potentially biholomorphic network, sometimes feature in the coordinate to the
yeah.
Things that are on the zero and then
Yeah.
So this is then sometimes minor.
It's very easy to include, and it also has been included in a recent paper by Berglund and collaborators, where they are basically doing that because they are addressing an interesting some interesting problems related to nearly singular Calabi-Yau manifests. Okay, so this is what I wanted to say about the package and how it works. Of course, the other packages will differ in what they predict, and also, codes don't look exactly the same. But I hope this gives you an idea of what these machine learning tools are doing, and then you can explore the package that you find most appropriate for your needs. And with that, I want to go into more advanced methods that talks a bit about how do we actually do things that are at least approaching the things that we need in string theory research. So in physics, for example, if we want to, as Lara was emphasizing in her lecture, if we want to compute what goes into our four-dimensional Lagrangian after a string compactification on a Calabi-Yau manifold, then we need the Calabi-Yau metric to compute certain things, and in particular, those features that we're interested in are related to interactions and masses of fields. So in order to do that, we want a method to compute the metrics that is general, so that we can pick the Calabi-Yau manifold that we like most and compute the metric on that. We don't want to be restricted to a quintic with a lot of symmetries on it, because that might not be the manifold that gives us the three chiral families of the standard model, say. So we want methods that work on different Calabi-Yaus. We want fast and robust predictions so that we can work through, maybe we want to work through many examples and do some sort of scan. We want to be able, so that's the reason for why we want this to be fast. We want it to be robust so that we can trust what we get. We are very, very interested in moduli dependence because there are lots of questions in string theory compactifications that has to do with the moduli of the Calabi-Yau. So these are the parameters that determine the size and shape of the Calabi-Yau. And just computing the metric at one point in moduli space will be okay for some things, but it's not the grand idea that we have. We want accuracy, and this accuracy can vary. So maybe for most points, we don't care too much. Maybe we're fine with something that is like, say, on the percent level or 0.1% or something like that. But once we zoom in on the points where we actually find the, the model that describes our universe, then we want to compute the electron mass to the, the accuracy that we have in experiments. So that's a lot of numerical control that we want to have that. So we want something that can be accurate, at least at these stable points in moduli space. And this is, this is just, dreams, the things that we would eventually need. It's not something that is realized. Then one can think of other things that we might want to do. So Calabi-Yau manifolds are geometric spaces where we can have interesting physics happening on submanifolds. So on certain regions, we might have some branes wrapping some submanifolds or so. And those branes in string theory can lead to interesting physics in their own right. And we might want to use the metrics on the Calabi-Yau to compute, for example, the volume of such cycles, which will then determine the mass of particles coming from wrapped branes. So those are just some things that we might want to do. And of course, people have thought about this for a long time, both using the new machine learning methods and before that using other numerical methods and any tool that is in the book, basically. So here I just wanted to list a few recent references using machine learning where these kind of questions are discussed. So for example, the moduli dependent metric has been discussed. It's a main target of the CY-JAX package is to do moduli dependence, in particular for the quintic, but with the aim of generalizing it beyond that in the future. To be efficient and accurate is something that's targeted by all packages, of course, but perhaps in particular by Yidis and Douglas papers and CY-JAX as well. CY metric, on the other hand, goes more for generality. So here we are developing methods to compute metrics on basically any Calabi-Yau manifold that you can think of. So we have been targeting some of the large databases of Calabi-Yau manifolds that exist. And then there are others, more advanced questions. So going beyond Calabi-Yau, computing spectra and so on, which I might have say something more on at the end of the lecture. Are there any questions about this? Yes.
Like a slightly de Sitter thing.
Right.
So is it like really?
So if I may rephrase the question, it's about the models where you're compactifying string theory on a Calabi-Yau will give you a Minkowski space from the setup. And then you need to do something more in order to get something that has a positive cosmological constant of the type that we observe. And this is certainly true. So one can imagine different things, and so there are different answers to this. So one is that, as James was saying here, yes, we do get Minkowski, but it is at a high energy scale. And then we will need to add more ingredients to this, which are some sort of perturbations, one or the other kind, and that will eventually break supersymmetry and give us something which is the sitter, one can hope. So this is you know, a very large field of research. There are all these very interesting models like KKLT, large volume scenarios. They have their flaws, they have their strengths, but it's an open problem, it's an interesting problem, and it's something where one would eventually have to fit this in some way. And then the Calabi-Yau metric would indeed be the appropriate thing to use because it's the thing underlying. You know, it's really Calabi-Yau-ness that is underlying this. One would have to think a bit about how to do with oriented foldings of the Calabi-Yau to be technical, but still, it's basically Calabi-Yau. Then there are the other constructions. So, for example, this SU3 structure manifolds. Those can be used either to give Minkowski solutions, or they can also be used to give ADS solutions, or well, I don't think one can honestly claim that they give de Sitter solutions, but this is another way of constructing compactifications where one can imagine that having these numerical tools or developing numerical tools for those kinds of examples could possibly give another approach to these questions. But so the quick answer to your question is yes, you're absolutely right. This is the models we have are Minkowski, and that is encoded into it. We need to add more things in order to get something that is more realistic on the cosmological scale. Okay, very good question. Yes.
So when you run your machine learning code, at the end, you get some parameters, right, for the metric. If you run it again, do you get the same parameters? Like, I mean, is there just a single minimum in the parameter space?
You mean the moduli, the parameters? You mean the parameters of
associated to the polynomials you have, in your metric
ansatz? Yes. Okay. So those are the parameters of the Calabi-Yau geometry. So the moduli. Yes. So in C1 metric, everything is done at a particular point in moduli space. So you pick it. For example, you pick the Fermat quintic as I did in the example, or you pick some other quintic. So that's specifying the complex structure moduli. And then you pick your Kähler modulus. We said here we wanted to keep the Kähler the volume fixed. So that's just one volume of Kähler parameter, controls the overall volume, and we wanted to keep that fixed during training. So indeed, this is something that's computed for a particular point in moduli space. There are these other methods that we will come back to, and that I just in a few slides, where you can train, say, predicting the Hermitian matrix H instead, and then you get something that is naturally moduli dependent with respect to the complex structure moduli within the range where in complex structure moduli space where you have trained it. So that's also something you can do. But this just means that you have computed the metric for these regions in moduli space, either a point or some region. It doesn't tell you that this is where you will end up, or that this is a stable region or anything. It's just saying, okay, you've chosen these parameters, and here is the metric. In physics, when we're doing string compactification, we have the idea that we want to be at a vacuum of the 10-dimensional theory, which will then, where the moduli will have some the potential that is created by some fluxes or something for the moduli will have a local minimum. And this is not something that these methods address at all. And in my mind, I think these are different questions. So I think it's separate. I think one would have to do moduli stabilization first and then compute the metric. But perhaps in the future, if we have super performant techniques, maybe one can try to do everything at once. I don't know. But at this point, I think one would have to find the region in moduli space where you want to be and then train there. And then maybe, if we know that there is a minimum somewhere and we want to look at fluctuations around that minimum, then we don't want to compute the metric only at the minimum, but at some region around. I don't know if the other experts in the audience want to comment on that as well.
Just say at any given point.
Yeah.
You always get them.
It wasn't correct. We didn't know.
Very similar, just quickly. Have you tried maybe using the free metric ansatz and see if that reproduces your other ansatz that you think that are the ones that should give you a Ricci flat?
No, I can't say that we have done that, that kind of comparison. But one could do that, of course. I mean, to really see, so to train the free model for as long time as you need, and then train, say, the phi network for a tenth of that time or whatever it would be required, and then compare the two metrics and see if they are the same. That's something one could do. I had not done it. Have you? Maybe.
I also haven't done it, but so what we did do is we trained one of these metric ansatz and we checked the sigma measure that you get for this ansatz. And then we compared with the sigma measure you get out of Donaldson's algorithm, so where you essentially optimize where you do this fixed point iteration to get these parameters in this H matrix. And from this, we could infer that you get the same sigma measure if you sort of included the polynomials up to degree 10 in this H matrix. So we know that sort of that at the level of the neural network that we work with, I don't know, three layers with 64 hidden nodes each, we reproduce essentially Donaldson's algorithm expanded on the basis up to 10, up to degree 10 polynomials. So we've done things like this. And then of course you could try to, I mean, if you have this phi network, you have the Kähler metric. So then you could try to fit, I mean, to read off the parameters in this basis that you expanded. But of course, as James pointed out, we don't know that just choosing these section bases is actually the most efficient basis to even use. And this restriction is not built into this phi network. So it's just choosing the most efficient one, or the best one it can find.
That's good. So as you're saying, you don't know the polynomial basis. Here you're approximating the function by this neural network answer. Have you ever compared it? It's like Hedrick is the best you can do with the other end.
Yeah, this is something you could do. We haven't done this. Yeah, we did compare it to Donaldson, but of course you could also just run Hedrick, see how low you can get, and see.
Something for you to do as a homework. Yeah. Okay, great. Yeah, great to have all these questions. So just some comments on these things. So moduli dependence, we've already talked about a bit. I just wanted to show some more examples of where this has been addressed. We've already said these things. Any Calabi-Yau, when we say the quintic, for example, it's really a family of Calabi-Yau manifolds. We have the parameters or the moduli that we need to take care of. And one should remember that if you want to machine learn the moduli dependence, if we are sampling points, for example, we're using the defining polynomial in doing that in order to solve for the points on the Calabi-Yau. So then the choice for moduli will enter there. So everything is dependent on moduli in a way. So here's one example from the same paper that I talked a lot about yesterday. So here's direct learning of the matrix H, which goes into either Donaldson's algorithm or Hedrick's algorithm, or Hedrick's minimization. We have one complex structure modulus, and what is plotted here is the absolute value of that complex structure. So it's a complex parameter. And here there are some experiments where dense models with varying number of hidden layers, but very few, 1, 2, or 3 layers, are trained over a range in complex structure moduli with simple dense layers, fully connected sigmoid activation functions. And the output is H in some particular decomposition. So it's not just the components of H, but it's some clever numerical way of outputting the data that I will not go into. And what we see here, in particular in the bigger graph, or in the bigger plot, is how this extrapolates over beyond the range where it was trained. So here we have trained data up to in the non-shaded part of the plot. James, please correct me if I'm saying something that is wrong. And so the model is trained from 10 to 100 in the absolute value of phi. And then you were looking at how this extrapolates up to 1,000. And what we can see here is that if we're looking at what you get from Donaldson, which is the green curve, so the solid green curve is what you get honestly from Donaldson, and the dashed one is the extrapolation. We see that these machine learned methods, they are performing pretty well, and they're doing better than Donaldson, even beyond the region where they were trained. So that's an interesting observation. Not, not to infinity and beyond, but still, roughly a factor of 2 over the range where they were trained. So that's promising. Another package which targets this modular dependencies, or a package which targets this modular dependencies, CyJax. And here I've just stole some plots from this paper from last year by Gerdes and Krippendorf, where they are again learning the H matrix, using training with Monchampel-Loss, but now they are working on a quintic with 2 complex structure moduli. So I just took the plots that were simplest to show here, because to sort of check that if you have 2 complex structure moduli, they're both complex numbers, and complex parameters, that means that you have a 4-dimensional real parameter space, and it's kind of more difficult to visualize that. So here it's, but here anyway, here's a sort of a sketch of what their networks look like. They're encoding the 2 complex structure moduli into some. They are doing some feature engineering here, so they are taking powers of that. They're putting it into some products of all combinations of powers, as you see here, and then they're taking real and imaginary parts of that, and then they're feeding that into a neural network which has different activations functions and different connections between the layers. What's shown here in the plots are the training loss and the training time, and the sigma accuracy plotted against training time for these networks. You can see that in an hour you can get a 1 order of magnitude improvement in both of these, in both the loss and the error measure. And so there is some work going on here, looking more into modular dependence and trying to see how far one can push that. Okay, accuracy and symmetry is something that I think I will just skip. This is related a bit to this feature engineering that Fabian told us about, and then I will just say a few things in the last 10 minutes about how in CY metric we are attacking other kinds of manifolds than the Calabi-Yau, than the quintic Calabi-Yau. So the thing we need to care about then is that, so first of all, we need to remember where the most Calabi-Yau manifolds come from. So we do have the manifolds like the quintic, which are these simple spaces where you have one projective space and you have one hypersurface in that. So that gives you a unique Calabi-Yau threefold. And you can go up and down in dimensions. You can look at cubics, quartics, sextics, and so on, but that changes the dimension of the Calabi-Yau. So if we want to look at Calabi-Yau threefolds, then we need to do something different. So we can change our ambient space to become a product of projective spaces instead. And then we can add on more polynomials defining our ambient space, which means that instead of having a hypersurface, we're looking at something where we're crossing different hypersurfaces and we're looking at the intersection of those. So those are known as complete intersection Calabi-Yau manifolds. And they were classified by Candelas, as Lara said in her talk. This gives us roughly, I think it's between 7,000 and 8,000 manifolds. Then we can go to toric ambient spaces, similar to what we heard about in the talks about fauna manifolds. And focusing in on the Kreutzer-Skarke list, which is a particular type, then we have, what was it, about 30,000 or something. Many spaces to choose from. It also depends on what you mean. You can choose different kinds of triangulations of these polytopes, and it gives you lots of manifolds. So then there are challenges. So we have these many Kähler classes in general. So in particular, looking at the, if you have a CC in this way, you will have at least as many Kähler classes as you have projective spaces in your ambient. So if you have, 4 ambient space, 4 components of your ambient space, then you will have 4 Kähler classes or 4 Kähler moduli, and you need to control that when you are training. So you stay in the same Kähler class, because otherwise you're not finding the Ricci flat metric you're after. You might find some other metric in some other Kähler class, but you lose control of what it is that you're actually doing. So you want a loss function preserving the class of J of the Kähler form. And there are different ways you can do that. So James raised in his question the possibility of computing the integrals over, so the volumes of various cycles in your manifold. So you can look at 2 cycles. The volume of that you would compute by taking the integral of J, the Kähler form, or 4 cycles, then you have the integral of J wedge J, and so on. And this is something you can do. However, then you need to sample points on these manifolds of different dimensions, so which is a bit technically a bit challenging, and I don't think anyone has attempted to do that. So instead, what we did was to compute topological quantities that depend on the Kähler class. That depend on the Kähler you can write as integrals of Kähler forms wedged with certain other things. And that should stay constant if you stay in the same Kähler class. So what does that mean here? So here I'm writing the formula for the slope of a line bundle. So this is a bundle over the manifold, one-dimensional complex vector bundle. And it has a connection and a curvature, and the curvature is F, which is written here. So for any line bundle that I write down, I can compute this slope as the integral of J wedge F over the manifold. So this is a 6 form. I can integrate it over the manifold, and I get a number. This matches up. And this is something that has to be topological, one can show, and one can then compute it using known topological quantities of the Calabi-Yau manifold, which are the intersection numbers. They are the D, alpha, beta, gamma here. So this is something that you can compute for any manifold, any Calabi-Yau manifold. And then you have the Kähler moduli, the T's, and you have the charge of your line bundle, the K here, which tells you what kind of line bundle you have. So this is a topological quantity, and it should be the same for any J that is in the same Kähler class. So we can compute this with the forbidden studi Kähler form that we know. We can compute it with this predicted Kähler form, or the thing that we're learning with the Calabi-Yau metric, with the neural network, and we can compute it topologically. So this is something that we can control. So we wanted to use this to construct a loss function, and this is what we came up with here. So here is the loss function for the Kähler class preservation now finally, where we are computing the difference between these topological line bundle slopes with the predicted line bundle slope. And we're doing this, and we want to get a number. We want to get a scalar function out of this. So we are summing up these things computed in different points. However, because this computation of this slope involves an integral, we cannot compute it on a small number of points. We have to go beyond the small mini batches that we use in our training for all the other losses. So this, in order to implement this, we also had to revise the training loop. So we have a 2-step training loop now, where you, in every epoch, you will first run over all the mini batches, and then you will do one run over this bigger batch in order to compute the Kähler class loss. And then after training, of course, you want to check that things are looking good. So one thing you can check is that you can compute the volume of the Calabi-Yau, because this is something that depends on which Kähler class you're in. And you can compute also these line bundle slopes again. So we have an example here. It's particular Calabi-Yau called the bicubic. The ambient space is P2 times P2. It has 2 Kähler moduli. So we train this for various choices of such. So I should also say what we compute this for a basis of line bundles. So it's something one can think about a bit, and one can convince us it's not oneself that this works. So we did this for different choices of Kähler moduli and trained it and managed to get decent results where the training curves look good. So the losses are going down. The error measures are working nicely. And so this is what is shown in these plots here on the top. We have this Monchampère loss and the Kähler class loss on training data, and then we have the sigma measure on validation data in light blue, and you can't really see that because it's hidden by the training data plot. And here I also show this table here when we are checking that the volumes agree, and we see that they agree to the percent level. Yes, yes, you could. Yes. Oh, you do. Yeah, you just pick one connection. Yeah. I mean, it's just so it's just given to you by the total one. For this, I mean, we want this. Yeah. Okay. Yeah. Yeah. But it's not something that we want to optimize. I mean, it's not the line bundles that we're working with is the basis of line bundles. It's just something that we want to use as something given. So we don't want to change that. Yes. Yeah. It should be. Yeah. Okay. Yeah. I can see your point. That could there be an effect of changes in F between different computations during the training? So if F would change when we are computing this loss function, if F would change between the different points, would that have an effect? It's not something that I've thought deeply about. I do not think it would have a huge effect. Maybe it's something we can discuss more. I'm not sure that I agree, but maybe we can discuss that more later because I'm running very much out of time. Okay, the other thing I want to mention is that when we go to toric ambient spaces, the methods that we have for generating points will also need to be revised, because the method that we had before was relying on having projective ambient spaces. And in these projective ambient spaces, we were selecting points in a particular way, which basically came back to, we have good numerical routines for selecting points on spheres. So if you have a toric ambient space, then it's not immediate how you should do that. However, what we managed to show is that you can basically embed your toric ambient space in a very redundant way into projective spaces. And then you use more or less the same routines. So I'm simplifying this a lot now. So this is much more complex than I'm making it sound. But in principle, this is the gist of it. So basically, you are using the same kind of mathematical results, in particular this theorem by Schiffman and Seldich, which tells you something about how random sections over projective space are distributed. So the zeros of random sections over projective space are distributed. And this is what we're using, and this is what has been implemented in the code by Fabian and Robert. And then this relies on some functionality from Sage, because we both need to be able to handle toric ambient spaces, which requires, or to generate data for toric ambient spaces. This is nicely encoded in Sage. And also in this working with this redundant description, there is some need for solving equations. And then you might, if you want to solve this in the most honest way, then you need to do you need to deal with some Grosvenor basis decompositions, and this is encoded in the package as well. Okay, so basically this is just telling these things in a bit more detail, but I will skip all of that, and I will just show you that, look, it works. Here's the toric ambient space, and it trains, and we are very happy. But this takes longer, I should also say. So both generating the points take longer because the methods are more complicated, and training takes a bit longer, in particular, than working on the quintic. So for this particular example, it's written here. So train is point generating about 1 hour, and training about 3 hours. And it's so we've never. I mean, we've only worked with. I mean, I'd run most of my experiments on this laptop, which is not the most performant machine in the world, and then we have had some good desktop machines, but nothing beyond that. I mean, you don't need any clusters or anything for these experiments. This is not something that requires a lot of resources. Yes.
Then I have parallelized the point generator.
Okay. Yeah. That's very good. Yeah. So then that brings you down from 1 hour to minutes, which of course makes a huge difference. Okay, so that brings me to the end. So what I've said is that there are ways to use machine learning to predict Ritchie flat metrics on Calabi-Yau manifolds. This is of interest, for example, in string theory, but perhaps for those of you in the audience who don't care too much of string theory either, this can be of interest because you might use similar kinds of techniques for the problems that you care about. And this is just a summary of what people have done. So most work in the literature is done on the quintic with a couple of complex structure moduli turned on. There are also more general methods that work on other kinds of Calabi-Yaus. There is also a discussion, ongoing tests and so happening where people use symmetries, the Kähler constraint and so on to improve speed and accuracy of the methods. Of course, the outlook and open problems means the first point of that is to improve everything that has been done. I mean, there's definitely scope for improvement here for having even more general routines, as Fabian was saying here, parallelizing part of the code can bring down the computational time to significantly. But with that said, I must say that the packages that are available, they are very, very nicely written. So it's a very good starting point for continuous work. Generalizing this beyond the Calabi-Yau setting, using the metric prediction in physics or mathematics, and then as a final thought. Okay, so if you're not interested in string compactifications for some inexplicable reason, then one point you can take from this is that what we see here is that we can say, we know that neural networks are universal approximators, and what we do here is to take a neural net and interpret it, train it so that it becomes a complicated function. In this case, it's a Calabi-Yau metric, but maybe there are other complicated functions that you care about. Maybe there's something else that is, solving some equation that you're interested in, and where you could do apply the similar kind of techniques and find a solution to the problem. And with that, I say thank you for listening.
Lovely lecture. I made a mistake of sitting next to Andre. Are there any questions?
Are you able to talk a little bit about kind of how much of the Kreuzerstärke landscape is currently like feasible with the kind of newly implemented KS functionality here?
Right. So I think the honest answer to that question is that I don't really know. I haven't done systematic experiments where I'm trying to push the boundaries, to where these methods apply. But what I would say, just guessing, is that we can deal with manifolds that have, say up to 4 or 5 Kähler moduli. Complex structure moduli is not really an issue as long as you don't want to learn the complex structure moduli dependence, because it's just, you can, with CY metric, I mean, you can take any quintic polynomial and just throw it in and train, and it will not affect I have not seen that it will affect the training time in any significant way. So symmetry is not going to be an issue there, but for sure, when it comes to Kähler moduli, I would say that there is a limitation. Maybe Fabian has thoughts on this. No.
Thank you.
Any other questions? While people were thinking, can I just check, is it, at the moment, is it just CY-JAX that has moduli dependence sort of built in? Or?
Yes, as far as I know. How is it with the bihomogeneous holomorphic networks? No. Yeah.
Any other questions? If not, let's thank Magdalena again for a lovely lecture.
Thank you.